In the figure given below, two blocks of mass small m and capital M are connected through a light inextensible rope. Then find the tension in the connecting rope. Consider the coefficient of friction between the inclined surface and the blocks to be mu. Alright. In order to do this, let us first find the acceleration of block of mass capital M and the acceleration of block of mass small m. This is the FBD, the free body diagram for the block of mass capital M. Which are the forces acting on it? This gravitational force capital mg. If this is theta as well from geometry. So the component of mg perpendicular to the inclined plane will be mg cos theta. Along the inclined plane will be mg sin theta. Since there is a rope connecting the two blocks, let us consider for this moment a tension to exist in the rope like this. And since the rope is connected to this capital M, the tension will be acting in this direction. Since the block is moving down the inclined plane, let us consider the friction to be in the opposite direction, F1. The normal reaction will be perpendicular to the inclined plane like this, which is N1. What is N1? It is capital M G cos theta. What is F1? The friction will be mu times N1 or mu times mg cos theta. To calculate acceleration of this block, let us consider this to be the x-axis. So acceleration of capital M will be all the forces acting along x-axis put together by the block mass. So which are the forces acting along x-axis? Remember, the forces acting along positive x-axis will be considered positive, otherwise negative. So down the inclined plane is plus mg sin theta. Up the inclined plane will be minus t minus f1, that divided by capital M. Now simplify. Mg sin theta by M will give you g sin theta minus t by capital M minus f1 is mu times mg cos theta, that divided by M will give you minus mu g cos theta. Call this equation number 1 and keep it aside. Now let's look at the other block of mass small m. Which are the forces acting on it? This is theta as well. This gravitational force mg. Component of that perpendicular to the inclined plane is mg cos theta. Parallel to the inclined plane is mg sin theta. Along the rope, the tension is T in this direction, and since the block is sliding, the friction is in the opposite direction, F2, and this is the normal reaction N2. Well, what is N2? It is small mg cos theta. What is F2? It is mu times N2 or mu times small mg cos theta. Now, by the same principle, by applying Newton's second law, let us find the acceleration of small m. It is sigma fx by small m. This is our positive x-axis. Let us consider all the forces along the positive x-axis to be positive and all the forces along the negative x-axis to be negative. What do we have along positive x-axis? We have mg sin theta plus t, and along negative x-axis minus f2, that divided by small m will give you acceleration. Now let us simplify. This will give you mg sin theta by m or g sin theta here plus t by m minus f2 is mu mg cos theta, that divided by m will give you minus mu g cos theta. Call this equation number 2 if you like. Now, we know that these two blocks are connected by a rope. So, the acceleration of block of mass capital M and the acceleration of block of mass small m must be the same. So, A small m must be equal to A capital M, and if you equate them, you will see that g sin theta and mu g cos theta will get cancelled on the either side. What you have is only 2t by You will get T by capital M plus T by small m to be 0. And this is possible only when T is equal to 0, or the tension in the rope connected between the two blocks will be 0. There is another way of interpreting it. Do you see that the acceleration of block capital M and the acceleration of block small m will be the same, which means that the block at the bottom of the inclined plane is not pulling the other block. Their accelerations are simply the same. So why should there be a tension in the rope connected between the blocks? There need not be. So the tension in the rope connected is 0. The correct option for this question is C. The system shown in the figure is released from rest with a mass 2 kg in contact with the ground. The pulley and spring are massless and friction is absent everywhere. Then find the speed of the 5 kg block when the 2 kg block leaves contact with the ground. Force constant of the spring, which is K value, is given to us. Also consider acceleration due to gravity to be 10 meter per second square. Alright, what is happening here? There are two masses, 5 kg and 2 kg. There is a string connecting these two masses, but there is a spring in between as well. Initially, it is as though 5 kg mass is held and released. The initial extension in the spring is 0. Now when it is released, the 5 kg mass will go down and the spring extension will become non-zero and will increase, thereby giving more and more restoring force in the spring. The tension in the string connected to this spring is equal to the restoring force produced in the spring itself. When the restoring force produced in the spring increases, so does the tension. Now look at the mass 2 kg. Initially, what would be the free body diagram looking like? There is tension acting in this direction, there is normal acting in this direction, and there is gravitational force 2g acting in the downward direction. As tension increases, there comes a moment when tension becomes equal to 2g, and at that point of time, the normal force vanishes and the block 2 kg lifts off. And we are supposed to find the speed of the 5 kg block at that exact moment. Well, this is how the motion happens. Now, at that moment, when the tension becomes equal to the gravitational force on the 2 kg block in the downward direction, we can write T is equal to 2g in magnitude, which will give us 20 Newton. We also know that the tension in the string is equal to the restoring force produced in the spring, which is equal to Kx. Why are we calculating x value here? Simple. Later, we are going to apply the conservation of mechanical energy principle to find the speed of 5 kg block at this moment. And for that, we need this x value. So from here, 20 is equal to Kx, or x is equal to 20 by k, which is 40, or half meter. Now that we know the extension produced in the spring, let us look at application of conservation of mechanical energy principle. Well, when the 5 kg mass comes down by half a meter, the spring gets extended by half a meter, and that results in the loss in the gravitational potential energy of the 5 kg block, which gives an increase in the elastic potential energy of the spring and an increase in the kinetic energy of the 5 kg block. So, substituting the values, we get 5 kg into g into x on one side in magnitude. On the other side, we have half kx square plus half into 5 kg into v square. Now, let us substitute the values. G is 10 meter per second square, x is half, k is 40, x is half again, plus half into 5v square. Simplify further. You will get 25 on this side. On this side, you will get 4 and then there is 20. So, you will get 5 plus 5 by 2 v square, or you will get 5 by 2 v square equals 20. So, v square will become 8 and thereby v is equal to 2 root 2 meter per second. So, at the moment when the 2 kg block lifts off, the speed of the 5 kg block will be 2 root 2 meter per second. The correct option for this question is B. The bob of a pendulum at rest is given hit to impart a horizontal velocity square root of gl meter per second, where L is the length of the pendulum. Find the tangential acceleration at the point where the velocity of the bob is 0. Alright. The first question you should ask yourself is, where is the possibility of the velocity of the bob becoming 0? If the bob is going along the circular path, is it in this region or in this region? Call it region number 1 and region number 2 respectively. Obviously, it is in region number 1. So, let us consider a general position in this region, which we shall call B. Let us call this position to be A. List out all the forces acting on the bob and consider the observer on the bob itself. There is tension T acting along the string in the radially inward direction. There is mg, the gravitational force acting in the downward direction. If this is theta, from geometry this is theta as well. So, the component of mg cos theta acts in this direction, and a component mg sin theta acts along the tangential direction. The observer is on the bob, so you have to account for the pseudo force or the centrifugal force as well, which is mvb square by L in the radially outward direction. What do we need? We need the tangential acceleration. What is tangential acceleration? It is a ratio of all the tangential forces put together to the mass of the bob. But do you notice that the only force acting along the tangential direction is mg sin theta? So, you have mg sin theta divided by m, giving you only g sin theta. This is the tangential acceleration we need. But do we know the value of theta? Not yet. We need to know the angular position theta at which the bob can come to rest momentarily. In order to do that, we will apply the mechanical energy conservation principle. For what? For the motion of the bob from position A to position B. Why can we do it in the first place? It's because there is no non-conservative force doing any work here. The sum total of potential and the kinetic energy must remain same. So, if you consider this level to be the one where the gravitational potential energy to be 0, and it is the only kind of potential energy we are interested in this case. The height of position B with respect to A is this much. The length of the string is L. So, this is L cos theta, and this height is L minus L cos theta. Now, apply the principle. UA plus KA equals UB plus KB. What is the potential energy of the system or the bob at position A? It is 0. So, 0 plus half m into VA square, and that's equal to UB mgh, that plus half mvb square. Well, we are considering the bob to come to rest momentarily at position B. So what is VB? 0. So this term is 0. We can cancel M as well. We are finding in this case the value of theta. So half into VA square. What is VA square? It is already given to us. Square root of GL. Square that, you will get GL here. G into H. What is H? L minus L cos theta. From here we can take GL common out. That will give us 1 minus cos theta here. You can cancel GL and GL. Cos theta will turn out to be half, or theta is 60 degree. Now we know the value of theta, 60 degree. All you need to do now is to find the tangential acceleration, substitute that value of theta into the expression. What is A tangential? It is G sine theta. G value is 10 meter per second square. Theta is 60 degree, so sine 60 degree. And that will give us 10 into root 3 by 2, or 5 root 3 meter per second square. So the value of tangential acceleration of the bob is 5 root 3 meter per second square at the moment when it comes to rest along the circular path. The correct option for this question is A. Next, we have a simple, straightforward conceptual question. It says, what is the principle of conservation of linear momentum state? Option A, linear momentum of a system cannot be changed. Option B, linear momentum of a system cannot remain constant. Option C, linear momentum of a system can be changed only if internal forces act on it. Option D, linear momentum can change for a system if external forces act on it. Well, which one is it? You know that the conservation of linear momentum states that for a system, the linear momentum will change only when the external forces are acting on it. So, the correct option for this question is D. A man of mass 60 kg is standing on a platform of mass 140 kg kept on a smooth horizontal surface. The man starts moving on the platform with a velocity 2 meter per second relative to the platform. Find the recoil velocity of the platform. Alright, let us visualize what's happening here first. Here is a man of mass 60 kg and the platform is of mass 140 kg. And the man relative to the platform moves at a velocity 2 meter per second. What is 2 meter per second? It is his relative velocity with respect to the platform. So when he moves like this towards right, obviously the platform will move towards left. Why does it do so? Because the initial and the final position of the center of mass of the system should remain same. And why is that? It's because if you look at the system of the man and the platform put together, there is no external force acting on it along this direction. Let me call it to be the x-axis. Yes, there can be a frictional force between the man and the platform, but they are internal forces. Internal forces don't produce any change in the position of the center of mass of the system. We are supposed to find the recoil velocity of the platform. With respect to whom? With respect to a person on the ground. So let's do one thing. We will consider this to be the system where man is denoted by small m, platform is denoted by P, and he is moving in this direction with a relative velocity u, relative to what? Relative to platform. And let us consider the velocity, the recoil velocity of the platform to be in the opposite direction and in magnitude v. If you consider this to be the x-axis and observer to be on the ground. Who is the observer? He is on ground. And let's designate the observer to be capital G. In that case, do you see that the net external forces acting on this system of the man plus the platform put together along the x-axis is 0. It means that the net linear momentum of the system will remain the same. Whatever it was in the beginning must be the same at the end or at any point of time as well. So, Pi must be equal to Pf. The initial linear momentum must be equal to the final linear momentum. What was the initial linear momentum of the system when the man and platform both were stationary? Stationary with respect to whom again? A person standing on the ground. 0. I will consider all the velocities and the momentum along the x-axis to be positive and along the negative x-axis to be negative. In that case, let's look at the man's velocity. I want the mass of the man into the velocity of the man with respect to observer on the ground. That gives us the momentum. So what is the velocity of the man with respect to observer on the ground? I can write it as Vmg plus, now for platform, Vpg. This is the linear momentum of the platform with respect to observer on the ground. Now, what is mass of man? 60 kg. Let us write Vmg. Do we know that directly? No. But we can write that in terms of the velocity of man with respect to the platform. How? Vmg can be written as Vmp plus Vpg. And mass of the platform is 140 kg into Vpg. Alright. So you get 60 into what is the velocity of man with respect to the platform? It's given to us. How much is it? 2 meter per second. In which direction? Along x-axis. So I will consider that to be positive. Plus, what is the velocity of the platform with respect to the ground? We see that the platform moves along negative x-axis with velocity magnitude v. So I will write it to be minus v. I'm just following the sign convention that we decided to adhere to. Plus 140 into what is Vpg minus v by the same convention, of course, and that's equal to 0. Simplifying this will get us v that we want. You will get 120 minus 60v minus 140v equals 0, or 200v equals 120. Simplify this, you will get v to be 12 by 20 or 0.6 meter per second. What is it that we have got? We have got the recoil velocity of the platform in the opposite direction. So the final answer is 0.6 meter per second. The right option for this question is C.